solution-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Good day, everyone. We are very excited to be today in a new session of AI for Good, the Discovery series on AI for Biodiversity. This series represents a partnership between the International Telecommunication Union, the Convention on Biological Diversity, NatureServe, and the Alexander von Humboldt Institute of Colombia. My name is Maria Cecilia Londoño, and I will be moderating today's session. In the AI for Biodiversity series, we explore a multitude of exciting and creative applications of AI that advance conservation, monitoring of biodiversity, improve management, enforcement, and surveillance of protected areas, and much more. This series is important because the 17 SDGs are very much interconnected with biodiversity. We cannot achieve our goals without maintaining and restoring biodiversity. A degraded biosphere has consequences that go far beyond conservation issues and hit at the heart of human health and well-being. So we hope that this series not only inspires you and celebrates that many achievements and innovation by our wonderful speakers, but also serve as a platform to accelerate the sharing and upscaling of creative solutions and ideas. And of course, we welcome all of you joining online from around the world via AI for Good neural network platform. Welcome. So today's session is dedicated to support biodiversity conservation through the use of an AI assistant for poaching prevention. Wildlife poaching fuels the multi-billion-dollar illegal wildlife trade and pushes countless species to brink of extinction. To aid rangers in preventing poaching in protected areas around the world, Milind and Lily have developed PAWS, the Protection Assistance for Wildlife Security, that they will be highlighting how on-the-ground challenges necessitate novel research advantages in machine learning, AI and causal inference. We'll discuss how to effectively bridge the gap between research and practice, presenting results from field development in Cambodia and large-scale development through integration with the SMART, the leading software system from protected area management used over 1,000 wildlife parks worldwide. The PAWS project has initiated in 2013 and has been extremely effective in predicting poaching activities and recommending patrols against them. The project is the result of a decade-long collaboration on PAWS with NGOs, resulting in removing tens of thousands of snares set to trap endangered animals in Uganda and Cambodia. For example, this work led to a 5-fold increase in snare removals in Cambodia. The SMART partnership, a collaboration of major conservation agencies, has begun deploying PAWS in 800 wildlife parks internationally, bringing AI to the fight to save the lives of endangered animals all around the globe. PAWS was listed as a top tech of 2018 by Institute of Electrical and Electronic Engineers Spectrum. So with that, we are incredibly excited to introduce our two speakers for today, Milind Tambe and Lily Xu. Milind Tambe is Gordon McKay Professor of Computer Science and Director of Center for Research in Computation and Society at Harvard University. Concurrently, he is also Principal Scientist and Director for AI for Social Good at Google Research. Professor Milind Tambe has won numerous awards, including recognitions for influential papers and distinguished intellectual and artistic achievements. His work focuses on advancing AI and agent system for public health, conservation, and public safety, with a track record of building pioneer AI system for social impact. His research has often provided the first very uses of key multi-agent system models and algorithms in the real world, as it is the example we are going to see today with the PAWS system. Lily Xu is a computer science PhD student at Harvard, developing AI techniques to address environmental challenges. She focused on advancing methods in machine learning, sequential decision-making, and game theory for biodiversity conservation through preventing illegal wildlife poaching. Much of her research has centered around PAWS system to predict poaching hotspots. Lily co-organized the mechanism designed for social good research initiatives and served as AI leader for the SMART partnership. Her research has been recognized with Best Paper runner-up at AAIE, the Informs Doing Good for Good or Award, and a Google PhD fellowship. Milind and Lily, the floor is yours.
Thank you.
Thank you so much, Maria, for that kind introduction. Yes, so again, my name is Lily Xu, and I'm really excited to be presenting this work with Milind and Tambe about how we can really use AI to help protect wildlife all around the world. So what's at stake is the biodiversity crisis.
Lily, just to jump in very quickly, I stopped your share screen at the beginning so we could see your speakers. So you're not currently showing your presentation. Apologies for that.
Okay.
Perfect.
Okay, thank you. So yes, to get us started, we'll motivate our work with just a brief overview of the biodiversity crisis, in which populations of keystone species, such as rhinos, tigers, and elephants, as recently as a century ago, were fairly robust. But today, in just 100 years, those populations have declined about 96% across the spectrum, and all of these species are now in critical danger of extinction, and they could all be lost within our lifetimes. And recently, the UN released a global survey in which they found that 1 million species out of 8 million plant and animal species existing on this planet today are all in danger of extinction by 2050. So this is really an urgent issue, and if we don't act in our lifetimes, we could really lose these creatures which provide us so many ecosystem services, such as clean water, air, food security, planetary health, and more. And one of the primary elements that protect our biodiversity and help reverse the biodiversity crisis are protected areas. So currently, about 17% of the Earth's land is designated as protected areas. And we have a recent imperative that we want to reach 30 by 30, in which 30% of the world's land is protected by 2030, so just within the next decade. But unfortunately, right now, only 25% of protected areas have adequate resourcing. So it's really essential that not only do we expand this 17% of land to 30%, but we also ensure that they have sufficient resources, funding, so that they can conserve the wildlife and other species that inhabit these lands. So one of the primary mechanisms to preserve biodiversity in these protected areas are ranger patrols. So they'll go around these areas and protect against threats such as poachers, which come in and place snares to trap animals, illegal loggers, which are cutting down trees, illegal fishers, which are hunting marine wildlife, and so on. And right now we have about 300,000 rangers all around the world conserving these lands, but an estimated 1.5 million rangers will be necessary to provide adequate resourcing for the world's land. So we need a 5-fold increase in the number of rangers, which both requires that we increase the amount of funding and also make sure that these rangers have sufficient tools and information in order to go to the areas that are in most urgent need of conservation. So to help with these efforts, to both inform the rangers where they should be going so that we can really equip them with the information and tools that they need, Our research group has, over the past decade, focused on developing the PAWS system, the Protection Assistant for Wildlife Security, which is an effort to apply AI for wildlife conservation. That's really going from the raw information of where rangers are, where the animals are, helping rangers plan patrols, and then moving all the way to working in collaboration with conservation organizations to get this work implemented on the ground. So if we look at this entire pipeline, we start from raw data about where rangers have been, use machine learning to try to get information such as understanding where poaching risk is happening, use that information to plan actions that rangers can take on the ground. And this is using decision-making tools. And then after we've taken actions, we want to evaluate how effective our actions are to evaluate the impact of our strategy so that we can bring that back, collect more data and bring that back into our learning and planning process. And then finally, after we've iterated sufficient times and have converged to a solution that we've seen and proven to ourselves work effectively, then we can move all the way to a deployment and try to build systems at scale to maximize impact to the 8 million species around the world. So to just kind of give an overview of all the ways that AI can help safeguard biodiversity around the world, if we want to try to understand questions like, animal populations and understanding how these populations are changing, this is where we can use predictive AI, such as machine learning. And then if we want to ask questions like which lands should we conserve to maximize protection for certain species, these require decision-making AI techniques, such as online learning and reinforcement learning that we'll talk about today. And then when we're at the point of trying to do retrospective reflection and understand, did some actions that we take, such as designating an area as a community managed area for protection, does it actually cause the environment to change? Did we actually make an impact on elephant numbers, for example? This is where we have some action and we're trying to figure out the impact on an outcome. And then understanding this relationship is where we can use causal inference. So all of these techniques really require novel AI solutions that we'll talk about how all of the different ways that AI can help with conservation impact. So now I'll turn it over to Milind for a little bit more history about this work.
So for the past 15 years, my team and I have been focused on advancing AI and multi-agent systems for social impact, focusing on topics of conservation, public health, public safety. Our work in conservation started in 2013, as was noted earlier. This was due to an invitation by Global Tigers Initiative at the World Bank to come and speak at their event. And whereas I was speaking more from the perspective of AI and the work that we had done until now, until that point in public safety, I came to understand the critical threat that poaching presents to global tiger populations, and that the tigers, rhinos, and so forth, we are all trying to make them all extinct. And so how to prevent this using AI became a top topic. Soon thereafter, with the Global Tiger Initiative and the World Bank Initiative, we got an opportunity to go to Bangladesh for the second Global Tiger Stocktaking Conference. And there again, got more motivation to try to think about how AI could prevent poaching and help conserve wildlife. I should say that simultaneously, I was certainly influenced when the captain of India's cricket team and the biggest superstar in India all started speaking about protecting tigers. And so that certainly had an influence on my thinking. And at that point, we said, okay, we have to start talking about how we can really use AI for wildlife conservation. Next slide, please. So our first attempt was through an invitation by Wildlife Conservation Society to come to Uganda. So I visited Uganda, and the problem that was presented was how to reduce snaring in wildlife parks. So in parks such as the Queen Elizabeth National Park in Uganda, there's beautiful wildlife, but there's thousands of square kilometers that need to be searched for these snares or traps that are placed by the thousands to kill and maim wildlife. But if you can see just a hundreds of rangers that are trying to protect this massive area. You can see the amount of patrolling that they have to do. It's an extremely difficult task to find snares in this grass. So how can we help these rangers find these snares easily? Next slide, please. And thus was born PAWS, an AI system to assist rangers, as Lily said, to predict snare locations. So that's predictive AI, and to recommend patrol. That's decision-making AI. These are some pictures from our various applications of PAWS in Uganda, in Cambodia, an effort in Malaysia and others. And there's a nice picture of Lily holding up a snare in Cambodia. Next slide, please. So I will provide a big overview of PAWS, and then Lily will definitely drill down into details and exciting research that she has led in our group. So to give an overview here, consider a large park like the Queen Elizabeth National Park in Uganda. We divide this park into 1 kilometer by 1 kilometer grid squares. And now our job is to predict for the rangers where are the hotspots where snares may be found. So these are shown by these red dots. But given these thousands and thousands of square kilometers, we want to narrow down a small number of possibilities where we can predict the location of snares. Next slide, please. To that end, we take, in this case, 10 years of data from Uganda, where they have data on for each 1 kilometer grid square, whether snare was found or not in that particular time frame, the ranger patrol frequency in that grid square. And we can also calculate distance to rivers, roads, and villages for that grid square, area slope, area habitat, and other such features, and use all of these features in order to make a prediction of probability of finding a snare per 1 kilometer grid square. So we built this system in the lab and initially did some tests in the lab. Next slide, please. But these initial tests were certainly not sufficient to convince ourselves and our partners, Uganda Wildlife Authority and Wildlife Conservation Society, that the system worked. So to show the use of this system, to predictive power of this system, the first test that was that we conducted was to select 2 9 square kilometer areas. This is in the fall of 2016, shown there by these green dots in the 2 areas of Queen Elizabeth National Park. These were infrequently patrolled areas where rangers had not gone much. And here we said that if next month you go and patrol these areas, you will find snares. And so rangers started patrolling these areas, and every day we would get an email as to whether snares were found in those areas where we had made these predictions or not. And initially there was nothing found. And you can imagine that there were students, this test just happened to be 1 month before a conference deadline. For the students who were leading this effort, certainly this was a very interesting situation. If snares would be found, there would be a paper that they could write. If no snares, no paper. Then news came that a poached elephant was found with its tusks cut off. So we had predicted poachers were going to be active in this area, and now they had found a poached elephant, giving us evidence that indeed this is where poaching was happening. Then a whole elephant snare roll was found and removed. So poachers were active in the area where we had made predictions. They were killing elephants, but before they could kill the next set of elephants, we were able to find an elephant snare roll and remove it, which gave a lot of joy to our students and us. And following that, a whole set of antelope snares were found and removed. And so this clearly was a successful pilot test, and now it was time to do a large-scale test. Next slide, please. So to that end, we selected 3 national parks. One is Queen Elizabeth National Park and Murchison National Park in Uganda, and Shripok Wildlife Sanctuary in Cambodia. In each national park, we selected 24 areas. Lily led some of this effort. Actually, she wrote this paper that shows the results of all of these parks. And so in each of these parks, 24 areas were selected. And these were infrequently patrolled areas, so rangers were not going there. And now we made predictions that some of these are high-risk areas, more snares would be found, and some of these are low-risk areas, less snares will be found. These are predictions made by our PAWS model. And now rangers went to patrol these areas for 6 months, And then we said, what happened as a result? So what you see here is where PAWS made a prediction that there was a high-risk areas, more snares would be found, and where PAWS said it's a low-risk area, less snares will be found. So it's not as though just going to an area which is infrequently patrolled yields snares. You have to be accurate in making predictions of which are high-risk areas to save ranger patrol effort. And so given that PAWS is able to make these predictions accurately, this gives us a lot of confidence that PAWS can now be ready for the next stage. Next slide, please. Indeed, in Sri Pak Wildlife Sanctuary, as was mentioned, from 2018 to 2019, we saw the number of snare captures jump 5-fold. These are pictures from PAWS being deployed and the snares, pictures of snares that came back from captures led by PAWS predictions. And in 2021, in 1 month of March, 1,000 snares were found due to PAWS predictions. Next slide, please. So now we are on to this next stage that Lily is leading, whereby PAWS is now integrated with the SMART platform. We just discussed SMART as the software used by rangers around the globe. But SMART collects data and PAWS works with it, complementing all the effort that SMART does in its software by making predictions using this data of where snares will be found in the future. And we are very excited that now this combination of PAWS and SMART, because of SMART being used in 1,000 national parks around the globe, PAWS is now available at all of these different parks, and excited to see how PAWS would be useful to rangers as they put their lives on the front lines protecting wildlife. Next slide, please. One of the big points of our research is that we don't want to sit in our lab and build an AI system and say it's useful. We want to be on the ground with the rangers, understand firsthand what the challenges are, and then build a system that matches what is actually required. So these are all the pictures from our trips to different parts of the world. A concrete example is this picture that is shown here with myself in this orange shirt, patrolling in Malaysia. So right after our work in Uganda, we started making patrol recommendations for the Taman Negara National Park in Malaysia. And we started suggesting they travel in straight lines, just like we had suggested in Uganda. So we would keep saying to the rangers there that you should travel in a straight line from point A to point B, and they would say that this is not a good way to travel. So this was very confusing to us initially in the lab, because isn't the shortest distance between 2 points in Malaysia a straight line? So they said, please come down here and patrol with us. And so this is a picture from this patrol. Next slide, please. And what being on the ground revealed to us is that this is a very hilly terrain. And as a result, as you can see here, you have to walk along ridge lines, along riverbeds. So this is a highway system inside the forest that needs to be traversed. And this is how PAWS then was developed to allow patrols that are not just traveling in straight lines, but along all these ridge lines and along the riverbeds and so forth, so as to match what is actually required. So with this, I'm going to hand the control back over to Lily to discuss the next parts of PAWS. Thank you.
Thank you, Milind, for that really, really inspiring overview. From here, I'll delve a little bit more into detail about how the PAWS system works to predict poaching threat around the world, and then I'll look onto the future in more recent work that our group has been focused on in the past 3 years. That's really trying to take the system that has been shown to be effective on the ground and extend it to wider use cases and broader sets of goals for protected area management. So to just look a little bit more closely at Murchison Falls Conservation Area in Uganda, this is the site where in the pictures that Milind just showed, our group has visited on the ground. We've spent almost a decade working with Wildlife Conservation Society and Uganda Wildlife Authority to help conserve the plentiful species in the park. So Murchison Falls is home to 4 of the big 5 species, including buffalo, lions, elephants, and tiger. And also the endangered Rothschild's giraffe. And it is one of the largest protected areas in all of Africa. But snaring in Murchison Falls is unfortunately extremely rampant. So in these photos, there's actually a snare in every single one of the pictures. And I've highlighted in red where all the snares are located because they're actually very hard to see, as you can tell. So there's just kind of a small wire snare that even rangers who are patrolling these areas might easily miss because there's just so many of them and the park is just kind of full of this brush. To make this a little bit more concrete, recent estimates have estimated that in Murchison Falls, there are 4.2 snares per 1 square kilometer. And this park is about 5,000 square kilometers. So you can estimate that that means there are about 20,000 snares in this entire park. So that's certainly a lot of animals that could be trapped by poachers. But for this entire park, 5,000 square kilometers and about 20,000 snares, there are only 190 rangers to patrol Murchison Falls. So it's really critical for us to help these 190 rangers figure out where to spend their time most effectively to find these small, hard to find wire snares. So when rangers go on patrols in Murchison Falls, they'll carry GPS trackers with them to record where they've been and where they found instances of poaching activity. So each one of these brown dots indicates one GPS observation that rangers have made on their patrols across 6 years of data. So some of them might indicate biodiversity observations, such as where elephants have been, or they might indicate poaching activity, such as this is where you found a snare or a poacher campsite. So over here, we have over 7 years of patrol that we're looking at and over 100,000 patrol observations. But you can see that the patrol observations are not evenly distributed around the park. So there are some areas that rangers have spent a lot of time and they have a really good sense of what the poaching patterns might be. But other areas are in green. They have pretty much never visited even across these 7 years of patrol. So those are the places where you really want to understand, are there poaching hotspots, for example, that rangers are missing out on? And this is where, again, AI can help. So we take the historical patrol observations collected by rangers and we process it to make it digestible to a machine learning algorithm by splitting up the park into 1 square kilometer regions. So every pixel in this image corresponds to the 1 square kilometer area of the park. So then we can see which of those areas rangers have been and how much time they spent in each location. And then also where they actually found poaching activity. And then we take all the geographic information that we have available in the park that we think might be correlated with poaching threat. So we have human features such as where the roads are and where villages are. We have landscape features like where the rivers are, what the land cover is, what the elevation is, and so on. And we also have some temporal information about changes over time. So we know the vegetation, the kind of grows more intensely in the summer. We have precipitation, which changes cyclically throughout the year. And we have things like temperature, which might change kind of linearly over time with climate change, for example. And we add all this information into a machine learning model combined with the historical patrol observations to predict poaching threat at the park. So then we're able to generate a risk map as shown here that is really pointing out the dark red areas where we think that there's really high risk of poaching that rangers should spend more time in, and the white areas where we think there's lower risk of poaching that might not require as much effort. And I also want to point out that some of the areas where we're predicting to be high risk of poaching are not always the same as the areas where rangers have spent most time. And then also there are some places where rangers have patrolled more intensely that we're predicting to be lower risk. So it's really kind of indicating to us where we need to spend more effort and where we might be spending kind of unnecessary effort as this decision aid for rangers. And then after we had implemented these predictions and deployed the field test that Milind had presented, we were really excited about these results, but we were even more enthused to receive really positive feedback from our collaborators as well, with Rohit Singh, for example, who leads the Zero Poaching Initiative at WWF, saying, I'm super excited with these results. let's get this going in other countries too this year. So that's what we're doing by collaborating with the SMART Partnership, which is a consortium of 9 different conservation NGOs that manages and maintains this database system that's used by protected areas around the world, which right now enables rangers to view and query and organize their patrol records, but has no ability to really help predict or prescribe actions for them to take. So we've partnered with SMART to integrate our PAWS AI system into SMART so that rangers all around the world are able to generate these predictions, kind of meeting them where they are. They don't have to collect more data for us. They don't have to, use new technology for us. We're really meeting them where they are, integrating with the existing systems that they have, and then trying to build a decision aid that provides them additional insight into their management activities. And SMART is widely used by over 1,000 protected areas around the world. So PAWS is as well now available to these sites. But there are some parks on the SMART system that are similar to Murchison Falls that have plentiful historical patrol observations. There are other parks on SMART that are only just starting to build up ranger patrols. So we were chatting with Royal Belum State Park in Malaysia, for example, in collaboration with WWF. And we had talked about the previous results that we had in Uganda and Cambodia. And they said, oh, this is really awesome. We've started using SMART. We did all the trainings. And we're really excited to kind of ramp up our patrol activities and have better insights into the illegal activity happening in our park. Would you be able to kind of help us make these predictions so that we can do patrol planning? And we said we'd be really happy to work with you. So set up a data agreement, and they sent their data to us. But what we ended up finding is that they had very little data to work with. So whereas in Uganda, they'd been using SMART for a long time, it had 7 years of patrol observations for us to make predictions. Malaysia was only just starting up the SMART system. So there was over half the park that they had never been to before. They had less than a year of data. So this really pointed out to us that, okay, well, the system that we've built so far is not going to work well with all of the parks at the moment. So this really pointed out to us what we needed to focus on next as AI researchers. So for data-rich parks, such as Murchison Falls, we can leverage that historical patrol information to build good machine learning models to help plan patrols. But for data scarce parks such as Royal Belum State Park, we have to think about how to conduct patrols to simultaneously detect poaching activity, finding hotspots that they've already found, while also improving the predictive model by going to areas with high uncertainty. So if we were to translate this into computer science terms, this requires that we exploit areas where we have visited a lot in the past, while we also explore areas where there's a lot of uncertainty, where our model just has no information about. And this trade-off between exploration and exploitation is a common paradigm in a subfield of machine learning called online learning, which is used for a lot of recommendation systems such as Netflix and Spotify and Google Ads. But unfortunately, all of these kind of like digital settings where recommendation systems are used are very different than the poaching world. So they have a lot of data, they're kind of lower stakes. So if I mess up and recommend you a movie that you don't really like, nothing too bad really happens. You might choose to cancel your Netflix subscription, but we don't really lose all that much. However, in the real world, if I make a bad recommendation, that means elephant entire lives are being compromised. So we really had to develop new techniques in AI to accommodate all of the different constraints and challenges in the poaching setting. And then from there, in our subsequent conversations and subsequent thinking in the lab, in collaboration with these conservation organizations and with rangers, this question just kept coming off of, okay, well, if we find poaching hotspots and we start removing a lot of snares, poachers are probably going to stop going there, So how are poachers responding to our patrols, and how should we plan accordingly? So originally, we took the data that we had from Murchison Falls and Queen Elizabeth National Park and tried to first understand this question of how are poachers responding to ranger patrols? And what we found is that when rangers patrolled more, poaching activity in that area in the subsequent month declined, but there was a slight increase in poaching in neighboring areas around that patrolled spot. So this is indicating that poachers were really being deterred by ranger patrols, which means that the actions that we take today is changing the environment tomorrow. So we really have to plan proactively and anticipate what will happen. So this necessitates sequential planning, which often will, in AI, can use techniques such as reinforcement learning, which is very common for game playing settings, such as the famous works where we kind of like solved chess and played Go and StarCraft very effectively, and also used for robotics planning. But reinforcement learning kind of requires like a really good understanding of the environment. So in chess and Go, for example, we have like a very clear specification of everything that is going to happen. But in the poaching setting, it's very hard for us to have a precise understanding of the environment. So if we know that there's deterrence and we can estimate when we patrol more, poachers will be deterred by 17%. Even though we can kind of estimate that number, we don't know it super precisely. But instead, we might be able to say that it's within a range of 12% to 23%. So then we have this uncertainty interval, which means that we can't just use out-of-the-box reinforcement learning techniques, but rather we have to do some kind of robust planning that's anticipating that kind of uncertainty. And that, again, required us to develop new AI techniques that's really kind of starting from looking at this real world problem, understanding what doesn't work yet with AI, like why we can't just apply AI out of the box, and therefore help us prioritize what to focus on as researchers. But after we developed this robust reinforcement learning technique, we were really understanding from our conservation partners that this question of how do poachers respond to ranger patrols has never been super adequately answered in the past. So there was really no causal evidence of this question. And this is something that kept coming up because there's a growing movement in conservation of moving towards evidence-based conservation, and more donors and funders and governments are really asking us, show us the evidence, before we give more land to be protected areas, before we give more money to rangers, we want evidence that this is actually making a difference. And then we said, okay, we want to help you answer that question. We want to provide evidence that ranger patrols cause poachers to be deterred. But it's really hard to get at that kind of causal conclusion because we can't just conduct a randomized controlled trial. So typically in science, randomized controlled trials or RCTs are the gold standard to coming to some kind of causal conclusion. And if we just take the data that we have, we might get something correlative, but it's not, there might be kind of unmeasured confounders, some other variable that we aren't accounting for that's really, causing causing poachers to change their behavior, for example. But we can't conduct RCTs in a context like biodiversity conservation in protected areas, because first, it's very expensive to conduct a scientific experiment like this. But more importantly, the opportunity cost is too high, because if we stop patrolling one area of the park, then that leaves it completely vulnerable to poachers. So we might sacrifice a lot of animals in the process of trying to get at this scientific fact. But a second challenge that we have here is that we have unobserved outcome variables. As mentioned before, it's really hard to find wire snares in the park. So when rangers patrol an area and they find a snare, we know that there is poaching there. But if rangers didn't find a snare in the area they patrolled, we can't say confidently that there is no snare there. It could have been the case that they just walked by and missed it, or they went a day too early and poachers came the next day. So whenever we say that there's not a snare, we have to second guess ourselves and say, okay, what really is the case? So trying to overcome these two challenges of how do we get at a causal result and not just something correlative, and then also how do we understand, the outcome of whether or not poachers are changing their behavior if we can't directly measure that, are the two challenges where we had to use AI to help in this causal inference process. So the question that we wanted to answer here is, what is the effect of ranger patrols on poaching in the next month? But again, poaching in the next month, we don't directly observe. So I'm marking this dashed line to show that we aren't able to measure this specifically, and that is a challenge that we'll have to overcome. We're trying to understand the strength of this relationship. So we aren't able to look at how poaching is changing, but we are able to see kind of whether or not we detected poaching in the next time step. So detection, we are able to directly observe, and that depends on how much patrolling we did in that next month. But there are all sorts of unmeasured confounders that might kind of muddy these observations, and any direct relationship that we see in the data between patrolling and poaching or detections could actually be subject to some other confounder. So in order to overcome this confounding, we use a technique in causal inference called shock-based analysis, in which we recognize that something in the past a random shock to the system to create a natural experiment that enabled us to run causal inference. And actually, the thing that presented that shock were the AI field tests that we had conducted in collaboration with the Uganda Wildlife Authority back in 2017 that Milind had described. So we had generated these AI predictions of poaching probability, and then rangers went to these areas that we thought were high, medium, or low risk of poaching, patrolled for 5 months, and then saw kind of, okay, what actually happened. And as a result of these field tests, we changed poaching behavior, we changed patrol behavior in the park for a very concentrated 5-month period of time with some randomization, because we randomly selected from all the high risk areas, all the medium risk areas, and all the low risk areas. So what I'm visualizing here is that white indicates kind of business as usual. So if rangers can just kind of patrol the same amount that they usually did. And then all of the red areas are the places where they patrolled more than usual. So we can think of this as equivalent to a treated site using causal inference. And all the blue areas, we can think about a control site, like a that would actually be comparable to a randomized controlled trial. And then from all the treated sites, and all the control sites, then we can say, okay, well, these are all the areas, that might, that we could use as our treatment and control group. But still, the challenge of a potential unmeasured confounder persists here, because there could be some other factor that caused us to patrol the treated sites or the control sites more. For example, they might have been systematically closer to the roads for all the treated sites, which is why they were more accessible and we spent more time there. So we have had to use another technique from the statistics world called matching, in which we took all of the information that we had about the park and all of the intuition that we had from our conservation partners that said, okay, well, we think these are the other things that could be potential confounders that we must account for. So the things that we considered, that we made sure to account for as potential other confounders, were looking at how much effort were patrolled in each of these areas in the past, and how much were they patrolled during the shock, what's the typical poaching risk over there, and then what are some other landscape features that we think might really impact the amount of ranger patrols, such as how far are they to a patrol post or how far are they from the boundary. And we took all these variables and then picked sites from among the candidate treated sites and control sites to make sure that they were kind of otherwise the same. So by achieving balance across all 6 of these possible covariates, then that led us to create pairs of sites that we could otherwise treat as a twin study to really replicate a natural experiment and move towards causal inference. So that addressed the unmeasured confounders part of our challenge. So that's kind of step 1. But we still have a second challenge, in which the outcome variable is still not perfectly observed. So we don't get to directly see whether or not poaching happened, the effect of our patrols, but instead we only see whether or not we detected poaching. So this imperfect detection, where snares are really hard to detect, is the second challenge that we had to overcome. And what we used here is looking at the patrol data and recognizing that snares are indeed hard to detect, but the more patrolling that rangers do, the more likely they are of finding a snare. So we looked at the amount of patrol effort in the park against the probability of them finding a snare, and we found that as rangers patrolled more and more in one area of the park, so if they walked 1 kilometer, they have perhaps 10% likelihood of finding a snare, but if they walked 10 kilometers, they have 40% likelihood of finding a snare. So that the likelihood of finding a snare increases with more patrol effort, but with diminishing returns. So eventually it kind of reaches the point where if there's a snare, we've probably found it by a certain amount of effort. And that indicates to us that we can use the amount of patrol effort as a proxy for the reliability of our observations. So if rangers patrol at a high amount of effort by walking a lot, then we can really say, okay, well, we can use this as ground truth. So we integrated that into a machine learning model to really understand for the observations that we did, how close is this to ground truth, and then what would be the true probability of poaching as a result. And that enabled us to take this the treatment, which is how much patrol effort changed during this 5-month shock period, and then look at what we can now accept to be the true outcomes of whether or not poaching occurs, and then estimate this causal effect. And what we found is trying to get a number that really says how much poachers are changing in response to ranger patrols. So if this value is negative, we know that there's deterrence. We found indeed this value is negative. So poachers are being deterred by ranger patrols. And the confidence interval of this value is fully within the negative range. So we have statistical confidence. And this is indeed the first causal evidence of deterrence in the poaching context. So we are really excited about this. And to look a little bit more concretely at what this means, if we were to take kind of the average site in the park, the probability that there's poaching is about 21%. So if we just kind of do the same thing that we normally do, there's 21% that poachers will place a snare there. But in a month, if we patrol 1 additional kilometer in that area, the probability of poaching will go down to 12%. So we're really able to reduce poaching by about 40% reduction by increasing the amount of patrols. So this is both a significant amount, but also, again, the first causal evidence of deterrence in which we're actually able to give a number as to the strength of this. So we're really excited about these results, and there are all sorts of broad implications for the conservation planning world about what this means. So within parks, this really helps rangers determine where they should spend more of their effort, because they're able to say, okay, well, here are the places where not only do we think there's going to be high risk, but we also think that we're going to be able to deter really effectively. But then also we're able to use this as evidence for the parks, in which they're constantly saying, oh, these funders are asking us, you patrolled here, what actually changed as a result? And they're able to say, well, we reduced poaching by 45%. So this can help go back to donors and governments and say, yes, we really do need to keep funding rangers. Their work is super important and meaningful for our biodiversity implications. And in turn, all of these insights and new techniques also feed back into the AI and statistics world by giving us new and better models that we can use to prioritize our research in the future. So kind of zooming out a little bit more, this PAWS system that we've developed is now being broadly used to predict poaching risk in sites all throughout the world, across Central America, Africa, and Southeast Asia. We've been able to work closely with conservation partners working on the ground, including with visits to Belize, to Cambodia, to Uganda, to really kind of understand how the terrain changes in each of these areas, what their priorities and constraints are, and just the resources that are available to them. And throughout all of this, we've developed new AI techniques by focusing on the real world constraints and priorities that these conservation organizations have to develop new insights in machine learning, online learning, reinforcement learning, and causal inference to help make more informed decisions. And meanwhile, AI can also help across the conservation world to make better models to predict poaching threat, better evaluate the impact of our actions using causal inference, and use that to inform adaptive management, which is this growing priority in conservation. Just to summarize some of this, our work in causal inference, for example, provides the first causal evidence that major patrols do deter poaching. In fact, that we are able to reduce poaching by 45% with a 1 kilometer additional increase in patrols. And this is kind of this new exciting result that we're really excited to share, and that we hope will be of significance in the conservation world as well. And I'd love to close by just recognizing and thanking again our partners on the ground in Murchison Falls, who are really doing the critical work to safeguard biodiversity on the ground. Thank you so much, and I'll turn it back to Maria.
Well, thank you for this great presentation. I think this is amazing, your work. Congratulations, very useful, results of really impact in the management of protected areas. We have one first question from our neural network, and it's done by Jacob Willem. He asked, have you found features in high data parks that translate well to predicting poaching in low data parks? Perhaps ruggedness, distance to roads, etc.?
Thank you so much, Jacob, for this question. And this is something that we've thought a lot about because of the parks where we have low data. Ideally, we'd be able to take this data from parks where we have a lot more information and then extrapolate that over. And while we are able to kind of find important characteristics, so we've been able to notice kind of universally throughout protected areas that that accessibility, so distance to road, distance to patrol post, and distance to boundary are really important in how much poachers are going there. And then also water access, because being close to water both impacts where animals are going because they're always looking for a water source, but then also impacts where poachers are going because they need to, when they're camping out, they need to have access to water. So we are able to find those kinds of critical points and use that to make recommendations to rangers about just here is additional insight that you can bring back into the field. But as of now, we haven't been able to build a really broad model that incorporates data from all the parks because there's two primary challenges. One of them is that poaching patterns just change really dramatically across parks. So we can't build a generalizable model. The animals are different. The landscape is super different. One of them might be really have mountainous and have a lot of changes in elevation, while another might be a flat savanna. And one, might have elephants, another might have tigers, and it's just all sorts of different landscapes. But furthermore, all this data is really, really sensitive. So parks are not willing to kind of share information across countries because there's just too much of a fear that this information will fall into the wrong hands if it is released outside of the park. So there's kind of two constraints. One of them is more kind of geographic and circumstantial. The other is more of a political data sharing question. Those have been the two fundamental barriers that prevent us from just building one universal model.
Thank you. And there is another question from Jacob, and he asked, might low-cost radio equipment be useful for detecting metal snares through interference?
So I think I'll just go first and say that there are, this is a great question. So there are these ideas for using different kinds of equipment to help detect snares. Another idea is the use of drones somehow to be able to spot these snares and so forth. I think one of the issues is really being able to have this equipment on a large scale, or be able to maintain this equipment and so on and so forth. And given the funding and the resources that are available, so having additional equipment like this can be a problem for these parks. But for the specific idea, I'll have to understand more. But in general, what we've been told is to focus more on these human patrols and make them more effective. Although, obviously, the more we can do with AI to try to help them, that is certainly useful. But I'll turn this over to Liddy if she has any further thoughts.
Yeah, while low-cost equipment would be really valuable, we have to kind of, I think, recalibrate our expectations of what low-cost means in these settings. So in Sripak Wildlife Sanctuary in Cambodia, for example, the way that these GPS observations are tracked are every 30 minutes. And that kind of gives us an understanding of where the rangers are, but a lot can happen in 30 minutes. They can move pretty far. So we were asking them, is it possible to reduce the amount of time that time window to 5 minutes so that we can just get more precise understanding of where you are? And they said, well, we could do that, but unfortunately our batteries don't last long enough for our phones. If we're going on 4-day patrols. And we're like, oh, well, what about carrying battery packs with you? And I said, oh, well, we can't afford battery packs for our phones. We just don't have the budget for it. And that really just indicates to us, like, oh my gosh, like the resource constraint that they're working with. They can't even afford, battery packs for your cell phone that cost $10, for example. So we really have to kind of focus on these kind of like most low resource constraints and helping them with as low-tech equipment as necessary.
Yes, and I think you start talking about a very important issue, and is patrolling effectiveness. And that is key really for achieving goal 3 on the new global biodiversity framework, that is protected areas, not just well distributed for biodiversity representation, but also well management. And given all the restriction that natural protected areas have in budget and their big size in many countries, this patrol effort is key to optimize. So I think some of the following questions are regarding this topic. We have one question from Rodrigo Agenel, and he first congratulates you about the fantastic work and talk. And he wants to ask you, if you have been able to assess the effect of group on detectability. So, are 2 rangers patrolling 1 kilometer together the same that 1 ranger patrolling 2 kilometers? And he asked this because he thinks it's important for patrol planning.
Thank you so much, Rodrigo, for the question. And I think that I think that typically there are other constraints other than just patrol effectiveness that come into play when they're thinking about ranger team sizes. So as I understand, they'll never really have 1 ranger patrolling by themselves because it's a really dangerous setting. First, because of just the landscape. These rangers are out in the wilderness for 4 days. So oftentimes, rangers will catch malaria, they'll get sick, they'll get injured. So it's kind of a safety thing for physical safety to make sure that they aren't going out by themselves. So oftentimes ranger teams are at minimum 4 rangers will go on patrol at once, just in case anything happens, like they don't want to be by themselves. So I think those other like real world constraints are oftentimes the bigger barriers, other than just thinking about can we, maximize the amount of coverage that we're taking out. They just kind of they can't split the ranges out too much, unfortunately.
So keeping up a little bit with the discussion about patrol optimization, have you thought of any other, situation that could be resolved using these algorithms, AI, that you have been developed so that other needs, not just poaching control, can be addressed for data managers at the same time, like putting other management issues inside so that we can be effective. Like I go patrolling for just not poaching, but for other reasons too, and make it more efficiently.
Yeah, so in the past, we have also applied the same model towards trying to prevent illegal fishing. And so to help patrol seas, so this was done for the United States Coast Guard. So how can we assist them in trying to prevent illegal fishing? And a similar model to PAWS works in that context as well. We're using past data about where traps are set. We can make predictions about where this illegal fishing might occur in the future. Same with illegal logging. That's a project that we are again launching, that we hope again the same sorts of techniques can be used. So where there is this sort of environmental crime, where there's past data that allows us to make some predictions and then use that to make recommendations to patrols, we can use this PAWS type model. But thank you for that question. That's a very important question.
Great. Now we have another set of questions more related to the biodiversity aspect of all this. And so one question we have from Vivek is, if you have had a combination, or have you used data from camera trap, like animal density, to improve the model?
So I'll say a little bit, and then Lily has a lot more to say about it. So in the past, we have tried to explore the idea of using drones with real-time information, not necessarily camera traps, but the similar, to help with trying to prevent poaching. And so the idea here is that the drones are used to look for poaching events, and this real-time data can be helpful for PAWS in allowing rangers to be reallocated. So in general, the idea there is not to arm the drones or anything like that. It's much more just to observe the poachers, at best to deter poachers by sending some deceptive signals, by turning on the lights in the drone or things of that nature. And so those are things that we have explored and have, and people have explored with drones to make noise with the drone or something like that. But you have to do this in a strategic fashion so that the poachers really think that rangers are coming in order to, and then deters them. So stop there. I know that Lily has a lot to say about camera traps, so I'll hand this over to her.
Yeah, definitely having as much auxiliary information and closer to real time as you can get is really helpful. Typically, most parks aren't able to have a broad array of camera traps that are evenly distributed throughout the park. And oftentimes, the places where the camera traps are also correlated with where the rangers are already spending a lot of time. So what PAWS is really focused on is for those areas that there's not much resources, where there haven't been much historical information collected yet, how can we extrapolate to those other areas? Which is why, instead of just kind of like slow scale things such as camera traps, oftentimes we turn to that global scale auxiliary information, which often comes from remote sensing. So with remote sensing, we can get daily or weekly information about what the land cover looks like, if there's deforestation happening, what the precipitation and vegetation indices look like. So remote sensing information is something that we are currently incorporating into our model to give us this broad scale overview of the entire parks that we're looking at and how that information is changing on a weekly or monthly basis to inform better models. But there's also other work that is currently being done that's really trying to develop good AI techniques to better analyze our camera trap information. So that's another area in which AI is being used for biodiversity conservation.
Okay, so I was wondering, all your maps are presenting the prediction inside the protected area. I was wondering, have you make this prediction also outside protected areas? And because obviously movement of animals and poachers do not limit to protected areas. And also if your results have been also, let's say, compared to the condition of the population of the species that have been purchased. So because I was wondering, maybe the poachers could go just outside protected areas and be having the poaching, although it's not happening inside, and then the results. How have you been able to analyze a little bit this situation?
So when we do make these predictions, we often will include a buffer zone where we're not just predicting for the park specifically, but we'll include the 5 or 10 kilometer buffer around that protected area, because certainly, animals and poachers are not going to confine themselves to a line that we draw on a map. So that is something that we're accounting for. And kind of the question of how do we determine the limits of a protected area is one of those critical considerations by our conservation collaborators. And there's a lot of discussion over kind of where these boundaries should be drawn, which areas should we extend the protected area to maximize coverage for important habitats for these animals. So that certainly is something that we're thinking about, and the conservation organizations are also considering. And then for your question, Maria, about species, I think that's really, really important, because oftentimes poachers are placing the most number of snares for kind of deer and pig and other bushmeat. So in the example that Milind had presented earlier about our field test in Richland Falls, they found kind of 1 elephant roll and 10 antelope rolls. So that kind of ratio is common in that, the majority of the snares will go to antelopes, and then some of the snares will go to elephants. So if we wanted to just find as many snares as possible, we would just remove the antelope snares and be done. But what we really care about for biodiversity conservation is conserving the most vulnerable species, such as elephants. So we also had work that's developing new AI techniques to help us understand that the species priorities that conservationists care about, in which we, rank elephant as the most important, and then perhaps, giraffes as the next important, and then deer and pigs as lower priority, for example. And then that can that prioritization metric then becomes a factor into our decisions. And now we're trading off, okay, how much do we care about finding as many snares as possible? And how much do we care about making sure that we're focused on the ultimate goal, which is preventing species from going into extinction?
Great, thank you. We have more questions from our neural network. These have been really a very a rich session and questions. Now we have Maria Rosa asking. First, thank you for this great talk. And she was wondering if you could tell a bit more about how, when you measure the impact of your tools, for example, number of snares found in 1 year versus the next, do you account for change in poaching patterns? For example, if the poaching has increased in general. And I think this also has to do a little bit to some other variables that are more related maybe to social variables that are out there. So that is a question.
So go ahead.
Yeah, thank you, Maria, for that very thoughtful question. And certainly when we want to measure the impact of our tools, we want to make sure that we're not kind of having some other things slip in, like if if we're saying, oh yeah, we found many more snares, if just poaching is increasing broadly, that's we don't know whether we're finding more snares because of our AI tool, or we're finding more snares because there's just more snares, and the percentage of snares that we're finding stays the same. Which is why in the field test that we did in Uganda and Cambodia, we kept it a closed box experiment by going to low risk areas and high risk areas at the same time, and then comparing the number of snares we found in those high risk areas and the low risk areas for the same month. So if there were any changes happening between month to month or year to year, both the high risk areas and the low risk areas would be impacted the same. And this enabled us to have a much more confident assessment that any differences that we were able to measure was on account of the quality of our predictions rather than some different change that's happening over time. And I also want to highlight that this exact concern that you're raising about some other, confounding factor coming in and muddling the data is the whole motivation behind that second part of the work that we shared today about using causal inference to evaluate impact of ranger patrols on poaching patterns. Because if we aren't thinking through all of those possible confounders and other exogenous changes that might be happening over time, then we can't have any confidence in the conclusion that we're drawing of, yes, our AI predictions are predicting well, or yes, ranger patrols are deterring poachers, which is why we have to really think carefully and account for those possible confounders.
Milind, do you want to add something to that answer?
So the other part of the question, which I also wanted to point out, is that we have a game theoretic system in addition to our machine learning system that is combined in PAWS. And so this is not so much about evaluation, but the fact that in PAWS, the idea is not only to make a prediction about where there are poaching hotspots, but also when we patrol, how those hotspots might move, and anticipate those and make patrolling recommendations that use that anticipation. So otherwise, if we just say, go to the hotspot, that's just going to shift the hotspot to some other place. But the idea with the game theoretic patrols, which Lily shared earlier with reinforcement learning, is to say, make not only predictions of where the hotspots are, but how would they shift if we patrol, and then patrol taking those shifts into account. And so because we have to, it's a game in a mathematical sense between the rangers and the poachers that we are trying to resolve and make sure that we anticipate poachers' movement when we come up with our patrols.
Great. So I have one more question, and is I guess two. How is this initiative offers conservation practitioners more like support or training? How can a park that is interested in including this and using PAWS can contact you is through another person initiative, or is directly with you? And then the other question was, how is the plans of PAWS to work with the poachers? Do you have any plans, not with the patrolling, but with the poachers? Do you have any plans to maybe work with them? And this is, I am thinking because you, Milind, mentioned something about how the influence, someone influenced your thinking about using AI for conservation, these superstars. And then how could we influence poachers to really leave this practice?
So I'll make some comments about that and then hand this over to Lily to discuss, because she's the right person to contact for how to use PAWS and everything. So in general, there are these three areas as we understand it. In PAWS, we are focused on the source to try to prevent poaching. Second part is when there's illegal smuggling of animal parts or animal products from the source countries to destination countries where there's a demand. And so this illegal smuggling also needs to be stopped. And so that's also a topic that we have explored. And then finally, we want to do influencing in the demand countries in order to stop the demand. So it's stop the product at the source, stop the transportation, and then stop the demand. Obviously, we can't stop it, but we want to reduce it. And this influencing via use of celebrities or key influencers is something that would be very valuable. We have explored this sort of influence, trying to figure out who are the key influencers and so on in different public health contexts, but not so much in the context of poaching, although this certainly is a very important question to try to reduce demand of wildlife parts. So we are interested in all three. There is plentiful data that we could get by collaborating with SMART, and therefore that's at the source is where we are focused on. But we are very interested in reducing smuggling of illegal wildlife parts and also in reducing demand, and would be very happy to collaborate with researchers or organizations who are working in these areas. I'll stop there and hand this over to Lily about how people can contact her about using PAWS.
Yeah, thank you so much for your interest in our system, not just in terms of learning more about it, but also making sure that it is actually used and available to parks. So as we mentioned, PAWS is now integrated with the SMART platform. So for any park that is currently using SMART, PAWS is a plugin that you can install and you can get set up on the system to do all this like cloud computation and get these predictions on your own. And we would really love to stay in the loop as you're going through those results to understand kind of how you're incorporating those predictions into your protected area decision making on a daily or monthly basis. So please do get in touch with me over email, and we would love to learn more. And if there are other protected areas that you're in contact with that you think would be interested in using the PAWS system, again, we would be more than happy to chat with them, give them kind of an overview of how this works, and just get them connected with the right resources and setup to bring this into their protected areas as well. Thanks so much. We'd love to talk more.
Well, thank you very much. We do not have more questions. Millie and Lily, thank you very much for this interesting talk and a really example of AI for biodiversity in practice and motion. So thank you and congratulations for this great work.
Thank you so much, Maria, and to the audience for your thoughtful and engaged questions. We really appreciate it, and such an honor to be able to join this initiative at the UN ITU AI for Good Summit.
I second all of what Lily said. Thank you so much.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.
AI is a powerful tool.
summit can help ensure that artificial intelligence charts a course that benefits humanity and bolsters our shared values.